Yo, what's up guys? It's Lionel The Builder back again with another video. I'm getting back into shooting a video a day, trying to challenge and push myself. I was gonna do a morning coffee rant again, but then I said, you know what? I'm actually about to start building this game, so why don't I do a series of me building the game live? But then I also thought, you know what? I've been meaning to do this systems design video, right? And a conversation that I had with Scott Bismonger himself, one of my mentors, a guy who has been coding for 20 years, when he told me that he uses AI to code, not like, you know, like he needs to, but for productivity purposes, something that would take him a longer amount of time, you use the tool that you have, right? But of course his prompts have to be at a higher level than us lower guys, but still it gives me more knowledge that, okay, I need to learn the systems design stuff. I need to learn the, you know, .NET C# cloud type of stuff. I need to learn all of the fundamental concepts more so than the syntax, more so than the coding, right? And I think in the future, just like imagine how nasty they were at like counting with the notebook, pen and paper before the calculator came out, you know, and now because of the calculator, none of us really know like how to do stuff in our head as much, but it hasn't really taken away from our skills as people, and it has only added to our productivity, right? So now AI is another thing similar to that, but to do with coding. But in order to do the proper prompts, in order to do the proper, like, you know, configurations and building and stuff, you need to know the knowledge. So that's what we're going to get into here today, the knowledge. Sorry for the 2-minute long intro. Oh, also shout out to our sponsors today, 2020 Faces. They donated these hats for one of our events, so I got to shout them out, man. I still have some of these left over for the next one, but without any further ado, let's get into it. Systems design concept.
This complete system design tutorial covers scalability.
Shout out Free Code Camp, links in the description if you want to watch this without me pausing and giving my take. Let's go.
Reliability, data handling, and high-level architecture with clear explanations, real-world examples, and practical strategies. Hike will teach you the core concepts you need to know for a system designs interview.
This is a complete crash course on system design interview concepts that you need to know to ace your job interview. The system design interview doesn't have to do much with coding, and people don't want to see you write actual code, but how you glue an entire system together, and that is exactly what we're going to cover in this tutorial. We'll go through all of the concepts that you need to know to ace your job interview. Before designing large-scale distributed systems, it's important.
Let's get this right real quick. Hold up. Let's get this right. Get me out the way so we can see everything. Okay. That is better. I hope you guys got your notebooks, your iPads or something. Let's go.
Important to understand the high-level architecture of the individual computer. Let's see how different parts of the computer work together to execute our code.
Bruh.
Computers function through a layered system, each optimized for varying tasks. At the core, computers understand only binary, zeros and ones. These are represented as bits. 1 bit is the smallest data unit in computing. It can be either 0 or 1. 1 byte consists of 8 bits, and it's used to represent a single character like A or number like 1. Expanding from here, we have kilobyte, megabyte, gigabytes and terabytes. To store these data, we have computer disk storage, which holds the primary data. It can be either HDD or SSD type. The disk storage is non-volatile. It maintains data without power, meaning if you turn off or restart the computer, the data will still be there. It contains the OS applications and all user files. In terms of size, disks typically range from hundreds of gigabytes to multiple terabytes. While SSDs are more expensive, they offer significantly faster data retrieval than HDD. For instance, an SSD may have a read speed of 500 megabytes per second to 3500, while an HDD...
You guys ever notice that it seems like when it comes to computers programs, systems, and design, it's really all about data. Correct me if I'm wrong in the comments. Is everything just about storing data, moving data around, transferring data from here and there, displaying it, breaking it down, reconfiguring it, pulling it back up? You know what I mean? It just seems like everything is all about data.
HDD might offer 80 to 160 megabytes per second. The next immediate access point after disk is the RAM, or random access memory. RAM serves as the primary active data holder, and it holds data structures, variables, and applications data that are currently in use or being processed.
Data. All the data gets stored in the RAM, right?
When a program runs, its variables, intermediate computations, runtime stack, and more are stored in RAM because it allows for a quick read and write access. This is a volatile memory, which means that it requires power to retain its contents, and after you restart the computer, the data may not be persisted. In terms of size, RAMs range from a few gigabytes in consumer devices to hundreds of gigabytes in high-end servers. Their read-write speed often surpasses 5000 megabytes per second, which is
the read-write speed, 5,000 per second. So that's when you're reading data, just seeing what it is, or when you're writing it, adding it in. Interesting.
faster than even the fastest SSD's disk speed. But sometimes even this speed isn't enough, which brings us to the cache. The cache is smaller than RAM, typically it's measured in megabytes. But access times for cache memory are even faster than RAM, often just a few nanoseconds for the L1 cache. The CPU first checks the L1 cache for the data. If it's not found, it checks the L2 and L3 cache, and then finally it checks the RAM. The purpose of a cache is to reduce the average time to access data. That's why we store frequently used data here to optimize CPU performance.
Genius design. Check the cache first before the RAM. And of course, it's all about data, and this is what makes performance. It's for performance optimization.
And what about the CPU? CPU is the brain of the computer. It fetches, decodes, and executes instructions. When you run your code, it's the CPU that processes the operations defined in that program. But before it can run our code, which is written in high-level languages like Java, C++, Python, or other languages, our code first needs to be compiled into machine code. A compiler performs this translation, and once the code is compiled into machine code, the CPU can execute it.
Okay, so of course we cannot write machine code. It's just straight ones and zeros. So we cannot technically write what the CPU reads, but we do write as a high level RAM code, which, you know, instructs that what to do, and then use a compiler in between from the RAM to machine code it into the binary. Okay, got it.
It can read and write from our RAM, disk, and cache data. And finally we have motherboard or mainboard, which is what you might think of as the component that connects everything. It provides the pathways that allow data to flow between these components. Now let's have a look at a very high-level architecture of a production-ready app. Our first key area is the CI/CD pipeline.
I love this. I love this part here, because, you know, we're building apps, so we always need to take everything into account, right? All right. So first up is your CI/CD pipeline.
Continuous integration and continuous deployment. This ensures that our code goes from the repository through a series of tests and pipeline checks and onto the production server without any manual intervention. It's configured with platforms like Jenkins or GitHub Actions for automating our deployment processes. And once our app is in production, it has to handle lots of user requests. This is managed by our load balancers and reverse proxies like Nginx. They ensure that the user requests are evenly distributed across multiple servers, maintaining a smooth user experience even during traffic spikes. Our server is also going to need to store data. For that, we also have an external storage server that is not running on the same production server. Instead, it's connected over a network. Our servers might also be communicating with other servers as well, and we can have many such services, not just one. To ensure everything runs smoothly, we have logging and monitoring systems, keeping a keen eye on every micro interaction, storing logs and analyzing data. It's standard practice to store logs on external services, often outside of our primary production server. For the backend, tools like PM2 can be used for logging and monitoring. On the front-end, platforms like Sentry can be used to capture and report errors in real time. And when things don't go as planned, meaning our logging systems detect failing requests or anomalies, first it informs our alerting service. After that, push notifications are sent to keep users informed, from generic something went wrong to specific payment failed. And modern practice is to integrate these alerts directly into platforms we commonly use, like Slack. Imagine a dedicated Slack channel where alerts pop up at the moment an issue arises. This allows developers to jump into action almost instantly.
I'm definitely going to need to set that alert service up with my project that I'm working on. I'm going to add that to one of my tasks. Alert service. True. To the Slack connection. Cool. Interesting.
Addressing the root cause before it escalates. And after that, developers have to debug the issue. First and foremost, the issue needs to be identified. Those logs we spoke about earlier, they are our first port of call. Developers go through them searching for patterns or anomalies that could point to the source of the problem. After that, it needs to be replicated in a safe environment. The golden rule is to never debug directly in the production environment. Instead, developers recreate the issue in a staging or test environment. This ensures users don't get affected by the debugging process. Then developers use tools to peer into the running application and start debugging. Once the bug is fixed, a hotfix is rolled out. This is a quick temporary fix designed to get things running again. It's like a patch before a more permanent solution can be implemented. In this section, let's understand the pillars of system design and what it really takes to create a robust and resilient application. Now, before we jump into the technicalities, let's talk about what actually makes a good design. When we talk about good design in system architecture, we are really focusing on a few key principles. Scalability, which is our system growth with its user base. Maintainability, which is ensuring future developers can understand and improve our system. And efficiency, which is making the best use of our resources. But good design also means planning for failure and building a system that not only performs well when everything is running smoothly, but also maintains its composure when things go wrong. At the heart of system design are three key elements: moving data, storing data, and transforming data. Moving data is about ensuring that data can flow seamlessly from one part of our system to another. Whether it's user requests seeding our servers or data transfers between databases, we need to optimize for speed and security. Storing data isn't just about choosing between SQL or NoSQL databases. It's about understanding access patterns, indexing strategies, and backup solutions. We need to ensure that our data is not only stored securely, but is also readily available when needed. And data transformation is about taking raw data and turning it into meaningful information. Whether it's aggregating log files for analysis or converting user input into a different format. Now let's take a moment to understand the crucial concept in system design, the CAP theorem, also known as Brewer's theorem, named after computer scientist Eric Brewer. This theorem is a set of principles that guide us in making informed trade-offs between three key components of a distributed system: consistency, availability, and partition tolerance. Consistency ensures that all nodes in the distributed system have the same data at the same time. If you make a change to one node, that change should also be reflected across all nodes. Think of it like updating a Google Doc. If one person makes an edit, everyone else sees that edit immediately. Availability means that the system is always operational and responsive to requests, regardless of what might be happening behind the scenes. Like a reliable online store, no matter when you visit, it's always open and ready to take your order. And partition tolerance refers to the system's ability to continue functioning even when a network partition occurs. Meaning if there is a disruption in communication between nodes, the system still works. It's like having a group chat where even if one person loses connection, the rest of the group can continue chatting. And according to CAP theorem, a distributed system can only achieve two out of these three properties at the same time. If you prioritize consistency and partition tolerance, you might have to compromise on availability and vice versa. For example, a banking system needs to be consistent and partition tolerant to ensure financial accuracy, even if it means some transactions take longer to process, temporarily compromising availability. So every design decision comes with trade-offs. For example, a system optimized for read operations might perform poorly on write operations. Or in order to gain performance, we might have to sacrifice a bit of complexity. So it's not about finding the perfect solution, it's about finding the best solution for our specific use case. And that means making informed decisions about where we can afford to compromise. So one important measurement of system is availability. This is the measure of system's operational performance and reliability. When we talk about availability, we are essentially asking, is our system up and running when our users need it? This is often measured in terms of percentage, aiming for that golden 5 nines availability. Let's say we are running a critical service with 99.9 availability. That allows for around 8.76 hours of downtime per year. But if we add 2 nines to it, we are talking just about 5 minutes of downtime per year. And that's a massive difference, especially for services where every second counts. We often measure it in terms of uptime and downtime, and here is where service level objectives and service level agreements come into play. SLOs are like setting goals for our system's performance and availability. For example, we might set an SLO stating that our web service should respond to requests within 300 milliseconds and 99.9% of the time. SLAs, on the other hand, are like formal contracts with our users or customers. They define the minimum level of service we are committing to provide. So if our SLA guarantees 99.99 availability and we drop below that, we might have to provide refunds or other compensations to our customers. Building resilience into our system means expecting the unexpected. This could mean implementing redundant systems, ensuring there is always a backup ready to take over in case of failure. Or it could mean designing our system to degrade gracefully, so even if certain features are unavailable, the core functionality remains intact. To measure this aspect, we used reliability, fault tolerance, and redundancy. Reliability means ensuring that our system works correctly and consistently. Fault tolerance is about preparing for when things go wrong. How does our system handle unexpected failures or attacks? And redundancy is about having backups, ensuring that if one part of our system fails, there is another ready to take its place. We also need to measure the speed of our system, and for that we have throughput and latency. Throughput measures how much data our system can handle over a certain period of time. We have server throughput, which is measured in requests per second. This metric provides an indication of how many client requests a server can handle in a given time frame. A higher RPS value typically indicates better performance and the ability to handle more concurrent users. We have database throughput, which is measured in queries per second. This quantifies the number of queries a database can process in a second. Like server throughput, a higher QPS value usually signifies better performance. And we also have data throughput, which is measured in bytes per second. This reflects the amount of data transferred over a network or processed by a system in a given period of time. On the other hand, latency measures how long it takes to handle a single request. It's the time it takes for a request to get a response. And optimizing for one can often lead to sacrifices in the other. For example, batching operations can increase throughput but might also increase latency. And designing a system poorly can lead to a lot of issues down the line, from performance bottlenecks to security vulnerabilities. And unlike code which can be refactored easily, redesigning a system can be a monumental task. That's why
it's so important. The code that you're writing to cause all of these different components of the entire system design to work is easy to change. Easier because each component takes so much of code that if you go to change an entire component and the way that they all interact with each other, like he said, it's a monumental task. And that is why as you level up and you get into positions of leadership, and this is your job is to do the entire system design, it is a more important task, looking at a higher level overview of the entire thing.
Why it's crucial to invest time and resources into getting the design right from the start and laying a solid foundation that can support the weight of future features and user growth. Now let's talk about networking basics. When we talk about networking basics, we are essentially discussing how computers communicate with each other. At the heart of this communication is the IP address, a unique identifier for each device on a network. IPv4 addresses are 32-bit, which allows for approximately 4 billion unique addresses. However, with the increasing number of devices, we are moving to IPv6, which uses 128-bit address.
So it's not all about data. We also have networking and how computers communicate with each other. I mean, even though what's the communication? Data is being transferred, but still other things to think about.
Addresses, significantly increasing the number of available unique addresses. When two computers communicate over a network, they send and receive packets of data. And each packet contains an IP header, which contains essential information like the sender's and receiver's IP addresses, ensuring that the data reaches the correct destination.
Every time I hear IP header, I immediately get flashbacks and PTSD, of course, policy issues.
This
If you know, you know.
process is governed by the Internet Protocol, which is a set of rules that defines how data is sent and received. Besides the IP layer, we also have the application layer, where data specific to the application protocol is stored. The data in these packets is formatted according to specific application protocol data, like HTTP for web browsing, so that the data is interpreted correctly by the receiving device. Once we understand the basics of IP addressing and data packets, we can dive into transport layer, where TCP and UDP come into play. TCP operates at the transport layer and ensures reliable communication. It's like a delivery guy who makes sure that your package not only arrives but also checks that nothing is missing. So each data packet also includes a TCP header, which is carrying essential information like port numbers and control flags necessary for managing the connection and data flow. TCP is known for its reliability. It ensures the complete and correct delivery of data packets. It accomplishes this through features like sequence numbers, which keep track of the order of packets, and the process known as the three-way handshake, which establishes a stable connection between two devices. In contrast, UDP is faster but less reliable than TCP. It doesn't establish a connection before sending data and doesn't guarantee the delivery or order of the packets. But this makes UDP preferable for time-sensitive communications like video calls or live streaming, where speed is crucial and some data loss is acceptable. To tie all these concepts together, let's talk about DNS, Domain Name System. DNS acts like the Internet's phone book, translating human-friendly domain names into IP addresses. When you enter a URL in your browser, the browser sends a DNS query to find the corresponding IP address, allowing it to establish a connection to the server and retrieve the web page. The functioning of DNS is overseen by ICANN, which coordinates the global IP address space and domain name system. And domain name registrars like Namecheap or GoDaddy are accredited by ICANN to sell domain names to the public. DNS uses different types of records, like A records, which map the domain to its corresponding IP address, ensuring that your request reaches to the correct server. Or 4A records, which map a domain name to an IPv6 address. And finally, let's talk about the networking infrastructure, which supports all this communication. Devices on a network have either public or private IP addresses. Public IP addresses are unique across the internet, while private IP addresses are unique within a local network. An IP address can be static, permanently assigned to a device, or dynamic, changing over time. Dynamic IP addresses are commonly used for residential internet connections. And devices connected in a local area network can communicate with each other directly. And to protect these networks, we are using firewalls, which are monitoring and controlling incoming and outgoing network traffic. And within a device, specific processes or services are identified by ports, which when combined with an IP address create a unique identifier for a network service. Some ports are reserved for specific protocols like 80 for HTTP or 22 for SSH.
Oh, that's where SSH comes from. It's a networking infrastructure. I've only had to use that with like GitHub, you know, trying to connect my repo to my computer. But interesting.
Calls like 80 for HTTP or 22 for SSH. Now let's cover all the essential application layer protocols. The most common protocol out of the Now let's cover all the essential application
SSH, RPC, FTP, POP3, never heard of that. SMTP, that's emails, right? AMQP, MyQ, TT, WebRTC, WebSocket, and HTTP. If you know all of these, you're a real one. I've heard of 1, 2, 3, 4, 5 of them.
Application layer protocols. The most common protocol out of these is HTTP, which stands for Hypertext Transfer Protocol, which is built on TCP/IP. It's a request-response protocol, but imagine it as a conversation with no memory. Each interaction is separate, with no recollection of the past. This means that the server doesn't have to store any context between requests. Instead, each request contains all the necessary information. And notice how the headers include details like URL and method, while body carries the substance of the request or response. Each response also includes the status code, which is just to provide feedback about the result of a client's request on a server. For instance, 200 series are success codes. These indicate that the request was successfully received and processed. 300 series are redirection codes. These signify that further action needs to be taken by the user agent in order to fulfill the request. 400 series are client error codes. These are used when the request contains bad syntax or cannot be fulfilled. And 500 series are server error codes. This indicates that something went wrong on the server. We also have a method on each request. The most common methods are get, post, put, patch, and
Get, post, put, delete. Those are CRUD, right? Create, read, update, delete. Create being what? Post. Get being read. Update being put, and
delete. Get is used for fetching data. Post is usually for creating a data on server. Put and patch are for updating a record, and delete is for removing a record from database. HTTP is one-way connection, but for real-time updates we use WebSockets that provide a two-way communication channel over a single long-lived connection, allowing servers to push real-time updates to clients. This is very important for applications requiring constant data updates without the overhead of repeated HTTP request-response cycles. It is commonly used for chat applications, live sport updates, or stock market feeds where the action never stops and neither does the conversation. From email-related protocols, SMTP is the standard for email transmission over the internet. It is the protocol for sending email messages between servers. Most email clients use SMTP for sending emails.
So that's why when you're building an application, you need to set up a SMTP.
And either IMAP or POP3 for retrieving them. IMAP is used to retrieve emails from a server, allowing a client to access and manipulate messages. This is ideal for users who need to access their emails from multiple devices. POP3 is used for downloading emails from a server to a local client, typically used when emails are managed from a single device. Moving on to file transfer and management protocols, the traditional protocol for transferring files over the internet is FTP, which is often used in website maintenance and large data transfers. It is used for the transfer of files between a client and server, useful for uploading files to server or backing up files. And we also have SSH or Secure Shell, which is for operating network services securely on an unsecured network. It's commonly used for logging into a remote machine and executing commands or transferring files. There are also real-time communication protocols like WebRTC, which enables browser-to-browser applications for voice calling, video chat, and file sharing without internal or external plugins. This is essential for applications like video conferencing and live streaming. Another one.
Okay, I don't want to make this video too long. Looks like this is gonna be one of those part 3, part 4 type of series. I'm gonna pause, do some active recall on this on my own, reviewing my notes, because you can't try and soak it all in at one time. I do like this type of video though, because it's more of like a brief overview of a lot of things that you need to take into account, and I think that through repetition that this stuff is going to sink in. The understanding gets better as we continue to move forward, you know, with this type of work. The more we do, the more we learn, the more we grow. Coming at this every single day, you know, from now into infinity. I'm Lionel the Builder, and I'll see y'all next time. Peace.